calorimeter, I started talking about that. I'll finish that up today. What else? Here's expanded adiabatic. I didn't talk about the definitions of the different changes yet. When we start doing thermochemistry, as I said, it's a lot of definitions that we have to worry about. I'm just playing with the buttons here. I think I'm seeing the right one. And we started off talking about state properties, and so far the first one we got to was internal energy. And the big thing about the state properties I tried to emphasize was the fact that theoretically, at least, you can say the change in the state property is independent of the path. That means you just take the final value minus the initial value to get the change. The only problem, as your book points out, it's very difficult to evaluate these numbers because of all the different effects that are going on in this chemical system. But there is one thing we can do, and we talked about heat change. Q is equal to, I talked about the fact that delta capital T, delta lowercase t is the same number, but mass and the small c means specific heat capacity. In other words, these are all the different relationships you have to be familiar with. So that was the expression we had for the heat change. And we talked about Q calorimeter and Q reaction. Important thing to remember once the surroundings. But you do your calculations for the calorimeter because that's where you measure things. And this is basically the equation that describes the heat change in the calorimeter. The other thing we talked about, work. And we were specific to say B delta V. Okay. So those were, and then we went on to the first law of thermodynamics, because we can't measure these, but if you measure all the energy changes that occur to the system, it's equal to Q plus W.
Question?
Yes?
Now, when you say work system, is that work done by the system?
That's the work of this, yeah, in other words, if the system's doing work, the system is expanding, this is a positive number, right? So this comes out negative, and the internal energy decreases because the system is doing work on the surroundings. If this number came out positive, then it meant that the internal energy of the system is increasing. Remember I wrote that little table, and the book has that little table also. Yes?
So W is the work of the system, or?
Yeah, as opposed to the work of the surroundings. And the thing is, when you talk about, you always calculate things for the system, if possible, and then if you want to talk about the surroundings, you just change the sign. And so this, a lot of books just say W is equal to P delta V, and you have to remember which way it goes. Your book's a little more specific to make sure that you get the right sign for your answer. And everything in thermochemistry or thermodynamics depends on the sign of things. The big thing we saw, there's a big difference between an exothermic and an endothermic reaction. But you calculate the same number, but one of them will be calculated will have a negative sign. For the other type of change, you calculate it has a positive sign, same number. If you have the same temperature change or whatever. Okay. So anyhow, these two things are not state properties, but the combination is equivalent or equal to a state property. Okay. The other thing I like to do to verify that is to look at something like this. pressure versus volume. I'm going to start right here, and I'm going to say this is 10 atmospheres, 1 liter. Down here, it's going to be 10 liters, 1 atmosphere. Notice I'm working with the same system. One of the ways of thinking about it, you have a little cylinder in here with a piston trapping the gas in here. And so initially, the volume is way down here. It's 1 liter, and the pressure is 10 atmospheres. And what do you know from the gas law? Whose gas law? In other words, you keep the amount constant, the temperature constant. That's what Boyle said way back when in his Boyle's gas law. So here I have 10 liter atmospheres. Here I have 10 liter atmospheres when I multiply P times V. Now I can think of going from here to here by different paths. One of the paths is, suppose I guess I can move it now. Down here's my 1 liter state. Here's my piston pushing down. And suppose I put a pin up here where it's 10 liters. Here's the 1 liter state. And I put a vacuum here, so there's no external pressure. P is 0. I pull this thing out, what does the piston do?
Raises.
Ups up to 10 liters. Diagrammatically, what happened here, and once it got to 10 liters, the pressure went back to 1 atmosphere because that's PV equals the constant, okay? So essentially, in this change where there's a vacuum, P external, they sometimes say is 0, that means W was 0. The area under the curve, 0. The other way I can get to that state, again, I have the starting original condition. I put an external pressure of 1 atmosphere, okay? Now the piston is going to, I pull this out. Since it's 10 atmospheres in here, 1 atmosphere out here, it pushes up till it stops at the 10 liter stop point. So what I'm doing is going down to, I guess I should have drawn again. 1 line is good enough, now I got 2 bad lines. But I go down here to 1 atmosphere, it goes across there. That's the work that you do. And W is now going to be equal to minus P, which is 1 atmosphere, times, I guess I did that wrong, because what's the final volume? 1 liter, minus 10. So it's equal to plus 9 liter atmospheres.
Oh, is that supposed to say 1 liter? Because it looks like it says 10 liters at the bottom there.
Whoops, yeah.
Okay.
Wait a minute.
Yeah, 10 and 10.
Yeah, it went to 1 liter to 10 liters and 10 atmospheres to 1 atmosphere.
Okay.
So the initial volume was 1 liter, and the final volume was 10 liters.
Okay.
So it's always.
Okay.
So I got plus 9 liter atmospheres, and that's because the system, this was the question before again, was doing work and pushing this up. And I'll come back to something else I can do in a minute. But I'm going to do one more change quickly. Suppose I drop the pressure to 5 atmospheres. So it's down to here. Now if I take the piston out and I have 5 atmospheres here, you realize what it's going to do is go up till it gets to what? 2 liters, because P times V has to be 10. In other words, pressure volume is a constant. So if I keep the pressure at 5 atmospheres externally, it goes down to here, and it goes up to 2 liters. Then when I get to this point, I reduce the pressure here to 1 atmosphere, and it'll continue up to 10 liters. Okay. So now, how much work do I have? Well, for the first step, the external pressure is 5. I'm not going to put the units, is what I said, so I put P instead. So it's 5 atmospheres. The final volume was 2 liters. The initial volume was 10. I've got my minus sign here. And then, the rest of the time I had the external pressure of 1 atmosphere. The final volume was 10 liters. Oops, this was not. The final volume was 1 liter. And this is my minus sign on here. You have to be careful with the signs. One of the things, I see all the wrong signs throughout the problem, and people come up with the right sign in the final answer. And I always look at that, and I always put a big question mark on, but if you have the right sign in the final answer, you got the right answer, and I put a question mark. Either you knew what you were doing and changed the sign at the end because you knew it didn't come out right, or you didn't know what you were doing, and you were careless, and you just happened to end up with the right sign. So the question mark means, if you can keep doing this all semester, you're going to pass the course. If you mess up half the time, you'll get half the grade. Okay, so you have to know what the question mark means. Make sure you know what you're doing, because you came up with the right answer, even though the mathematics you put in the middle don't necessarily correspond. So I was already getting rid of my minus signs here, and I wouldn't really leave all the signs in so it looks right. So it's 1 atmosphere, and the final volume was. The final volume was 1 liter minus 2 liters, okay, because the initial volume right here was 2 liters, and it went up to 10. Oops. Let's say it right. Here, let's see, I'm using delta V, so my initial volume was 1 liter, and my final volume, I get this right. In other words, the initial volume was 1 liter up here, and then it went to 2 liters. And then it went from 2 liters to 10 liters, okay? So this was right here, plus what? 5, and over here plus 8, 13 liter atmosphere. So you see I got more work. And if I did it by doing a series of small steps like this, I get more and more work. And finally, if you do differential, if you do the calculus business and you do the differential, this will be W max, and you say you did it reversibly. In other words, you had the initial condition here, you made the pressure on the external, this pressure going down, you decrease it by a very small amount, the piston moved up. Note if you increase it a little bit, it goes down, so the piston can go back and forth. So you can describe that, that's a reversible process. And when you do it reversibly, and you put in the calculus where you put in PV equals nRT, you come up with some sort of relationship. Your book doesn't really do this, but some books do. So you can calculate the maximum amount of work. Other books do that. You don't have to worry about it because this book doesn't do it. And most of the new tests don't ask you to learn that anymore. So that was something we did a long time ago. But we could calculate the maximum amount of work by doing calculus. And that's going to be equal to a state property that we're going to get to later on. It's called the free energy change. It's the maximum amount of work you can get from the system. So if you do the work change reversibly, you get the maximum amount of work. It corresponds to integrating this thing, and you get some sort of curve like this, which has the log function in it. And we do other things with that, but we're not, as I say, this book doesn't do it, so don't worry about it too much. But the point is, you can do this, or you can describe different different paths that give you different amounts of work. The unique path is if you do the change reversibly. And then you do the differential calculus, or integrate, I guess, is what you do. And you come up with this final result, which can calculate the maximum amount of work, which is equal, eventually, as we'll see, to the Gibbs free energy.